Picture this. You are standing outside tonight, looking up at the black velvet sky. You feel the cool, immense silence of the cosmos. It's quiet, so quiet, you might be tempted to call it peaceful. But as we begin our story, you will discover that this silence is profoundly deceptive. It is not the quiet of peace. It is the subtle, vast sound of a force that makes every visible power look small in comparison. It is the sound of 68% of reality moving, accelerating, and slowly but surely reshaping the very structure of the universe as we know it. We observe the stars. We feel gravity holding us to the earth. We rely on the fundamental forces of nature that bind atoms together. This journey is the story of a force that, on the largest scales, seems to defy or overpower many of those familiar laws. A force that has no face, no discernible origin, and remains the greatest enigma in modern physics. It is, quite simply, dark energy. And its behavior poses perhaps the biggest unanswered question in cosmology. This is not merely a question of if the universe will continue to expand. It is a question of how its accelerated expansion will ultimately define its end state. As we explore the science, we will see that the force expanding our universe is the same force that, under certain theoretical models, could eventually overcome even the fundamental forces that hold matter together. This potential ultimate state of the universe is what physicists call the Big Rip. But the path to discovering this strange cosmic future began with what scientists first thought was a computational error. To understand this deep mystery, we must travel back to the late 1990s, to a time when cosmologists believed the final fate of the universe was settled. The prevailing theory was simple. The universe was expanding, but the relentless tug of gravity, fueled by all the visible matter and the unseen dark matter, must surely be slowing that expansion down. It was a clear, logical prediction. Like an object thrown high into the air, the cosmic expansion was expected to gradually decelerate. Two highly competitive astrophysics teams were racing to be the first to precisely measure this cosmic deceleration. They were looking for the slight braking effect that gravity was applying. Their primary tool for this immense measurement was the Type 1a supernova. Imagine the supernova 1a as the perfectly calibrated standard candle of the cosmos. Every single one of these exploding stars achieves a near-identical peak brightness. If you know the absolute brightness of a candle, you can measure its distance simply by how dim it appears. This gave the teams a crucial cosmic ruler to gauge how fast distant galaxies were pulling away. This meticulously collected data led to one of the most surprising scientific revelations of the 20th century. The teams expected to find the distant supernovae glowing somewhat brighter than the nearby ones, because they would be moving slower. But the precise data showed the exact opposite. The distant supernovas were fainter than expected. They were actually much farther away than the physics of a slowing universe allowed. The only logical yet deeply shocking conclusion was that the expansion of the universe was not slowing down. It was speeding up. It was accelerating. The discovery was so profoundly counterintuitive, so completely against the established model, that the researchers themselves initially suspected a fundamental flaw in their instruments or calculations. They meticulously checked their entire process, from the telescopes to the final data reduction. They spent months trying to disprove their own findings, fully aware that if the results held true, it would revolutionize cosmology. This period of intense scrutiny cemented the reality of the Great Acceleration. The results were eventually published in 1998, surprising the entire scientific community and earning the principal researchers the Nobel Prize. But the core finding remained. The universe was not just expanding, it was being driven apart by a pervasive force that was, on the largest scales, overpowering gravity. They named this invisible force dark energy. The realization quietly settled into the scientific consciousness. Dark energy is not a passive remnant, it is the dominant engine of our cosmic future. We are left to consider the sheer weight of that initial discovery. Imagine the moment of realization for a scientist like Adam Rees, one of the co-discoverers. He might have thought, the data is clear, almost too clear. We have measured the answer, and the answer is that the universe is not slowing down, it's accelerating. This acceleration, this new term in the cosmic equation, it changes everything. It means something unknown is out there, a vast, pervasive energy filling the void. We must understand the implications of this finding, as it means the ultimate destiny of the cosmos is far stranger than we ever imagined. Dark energy is the ultimate paradox. We know what it does, but we have very little idea what it is. It accounts for a staggering 68% of the total mass energy of the universe. Compare that to the less than 5% of normal matter, the familiar stuff that makes up you, the Earth, and every visible star and galaxy. Dark energy is the dominant factor, and its influence on the long-term future is absolute. The first, most elegant explanation for this invisible power was rooted in the work of Albert Einstein. Decades before acceleration was discovered, Einstein had introduced a term into his equations of general relativity called the cosmological constant, lambda. He initially needed it to counteract gravity and keep the universe static. When observations showed the universe was expanding, Einstein famously dismissed the constant. But modern physicists brought the constant back to explain dark energy. Lambda is interpreted as the intrinsic energy of empty space itself. It is the pervasive outward push of the vacuum. The elegant simplicity of this idea is compelling. As space expands, more vacuum is created, and therefore more energy is generated, which pushes space to expand even faster. A perfectly self-sustaining acceleration. Yet this simple explanation quickly faced one of the most profound puzzles in theoretical physics. The puzzle rooted in the fundamental difference between theory and observation. When physicists attempted to calculate the expected theoretical value of this vacuum energy based on the principles of quantum field theory, the resulting numbers were astronomically vast, defying easy comprehension. Quantum theory suggests that the vacuum of space is not truly empty, but is teeming with virtual particles, constantly popping into and out of existence, a phenomenon often called the quantum foam. This highly energetic activity should, in theory, imbue empty space with an immense amount of energy. The theoretically expected value of this vacuum energy was approximately 1 followed by 120 zeros times larger than the value of dark energy actually observed. This numerical difference is considered one of the most profound mismatches in the history of scientific calculation. If the theoretical amount of energy were correct, the universe would have undergone such rapid expansion that stable structures could never have formed. The sheer magnitude of this discrepancy suggests that the cosmological constant, in its simplest form, is either fundamentally incomplete or that some profound, subtle quantum mechanism is actively canceling out almost all of the theoretical vacuum energy. This mystery remains a central challenge in linking quantum mechanics with general relativity. Faced with the profound difficulty of the simple cosmological constant, cosmologists were forced to consider a more dynamic possibility. What if dark energy isn't constant at all, but rather changes over time? This led to the hypothesis of quintessence. The name, borrowed from the ancient Greek term for the fifth element, the pure, mysterious substance thought to make up the heavens, suggests something otherworldly. In modern cosmology, quintessence is hypothesized to be a dynamic, fluid-like energy field that fills all space. Unlike the simple, fixed cosmological constant, the density and attractive or repulsive nature of quintessence can change over the lifetime and expanse of the universe. This dynamic nature introduces a new critical variable into our models. The behavior of a fluid like dark energy is described by its equation of state, a crucial parameter often represented by the Greek letter omega. This ratio of pressure to energy density acts as the cosmic destiny dial, determining the ultimate fate of the universe. If omega is equal to -1, the energy density is constant, aligning with the simplest model. If omega is greater than -1, the energy density decreases as the universe expands, leading to the predictable cold fate known as the Big Freeze. But if omega is less than -1, if this quintessence field's pressure is more negative than its density, it means the energy density increases as the universe expands. This third and most dramatic scenario, where omega is less than -1, is called phantom energy. And phantom energy is the physical condition that leads directly to the Big Rip. The dynamic nature of dark energy means the future of the cosmos is not fixed, but hinges on the subtle value of this variable. The dynamic nature of dark energy means the future of the cosmos is not fixed, but hinges on the subtle value of its equation of state, omega. Now we turn our attention to the constant power struggle that defines our existence. The cosmic battlefield defined by dark matter and dark energy. We live in a cosmos defined by a constant, profound tug-of-war between two immense forces that remain invisible to our eyes. Dark matter, which accounts for approximately 27% of the total energy mass, is the architect. It is the invisible scaffolding, the gravitational glue that was instrumental in building the cosmic web. It forms vast, stable halos around galaxies. Without its powerful gravitational attraction, the rapidly spinning galaxies would have simply flown apart. Dark matter represents the force of cohesion. It is the energy that seeks to bring and hold things together, the foundation of all large-scale structure. Dark energy, accounting for the dominant 68%, is the wrecker. It is the force of expansion. It seeks to push everything apart. It represents the overwhelming majority of the universe's content, and its influence on the long-term future is absolute. For the first 7 billion years of the universe's existence, dark matter was largely in charge. Gravity ruled supreme. Galaxies clumped together, forming the magnificent clusters and superclusters we observe today. But around 5 billion years ago, remarkably close to the time our own solar system was forming, the energy density of dark energy finally surpassed the combined matter density. Dark energy had achieved cosmic dominance. The universe entered the dark energy-dominated era, an era of accelerated expansion that continues to define our existence today. Dark matter diligently built the structures, but dark energy simultaneously ensures that every newly formed galaxy cluster is immediately pushed further away from every other cluster, slowly turning the cosmos into a vast, cold expanse defined by ever-increasing distance. But even this cosmic acceleration is merely the initial phase. The Big Rip is the catastrophic moment the Cold War turns hot and dark energy turns its destructive attention from the spaces between structures to the spaces within them. It occurs only if dark energy is phantom energy, meaning its equation of state omega is definitively less than -1. This is the doomsday threshold. If omega is less than -1, the crucial physics dictates that the density of dark energy increases as the universe expands. It is a profound cosmic abnormality. It becomes stronger the larger the volume it occupies. It is literally feeding on the very expansion it creates, leading to an exponential and unstoppable acceleration. This force would then sequentially overcome all other fundamental forces one by one. The Big Rip is the predicted end where all 4 fundamental forces are defeated and every single constituent part of the cosmos is violently torn apart. The Big Rip is the predicted end where all 4 fundamental forces are defeated and every single structure in the cosmos is eventually violently torn apart. How long would such a catastrophic countdown last? The answer depends entirely on the current precise measurement of the cosmic destiny dial, omega. The closer omega is to -1, the longer the countdown extends, possibly for trillions of years. But the more negative it is, for instance, if omega were -1.5, the faster and more violently the end approaches, potentially condensing the timeline significantly. Current observations place the value of omega very close to -1, but the possibility that it lies slightly below this threshold remains a key driver for future research. Let us explore a scientifically plausible scenario based on models where omega is slightly less than -1 to visualize the stages of this destruction. Phase 1. The galactic breakup, 60 million years before the end. The accelerating force of dark energy finally overcomes the gravitational pull that binds galaxy clusters and superclusters. The vast, magnificent structures built by the gravitational cohesion of dark matter over billions of years are dissolved. Our own local group of galaxies, which includes the Milky Way and Andromeda, will be unbound. All other galaxy clusters outside our cosmic sphere will recede so fast that they will disappear beyond our cosmic horizon. The gravity exerted by the massive halos of dark matter, the foundation of these clusters, is the first fundamental casualty. The cosmic web, the masterpiece of the architect, is actively unstitched as the expansion overwhelms the force of cohesion. Phase 2. The Milky Way's execution, 50 million years before the end. The force accelerates, beginning to tear apart the Milky Way galaxy itself. The gravitational hold of the central supermassive black hole is finally defeated by the repulsive force. Our star, the Sun, along with every other star in our galaxy, is violently flung outward into the ever-expanding void. The dark matter halo that gently cocooned the Milky Way is next. The density of dark energy locally overwhelms the dark matter's gravity. The halo is actively pulled apart from the center, and the stars, once held securely in orbit, are now freed and hurled away. Phase 3. The solar system's collapse, 2 months before the end. The force of dark energy becomes so immense that it defeats the gravitational pull of the Sun on its planets. The Earth, Mars, Jupiter, and Saturn are all ripped from their stable orbits. They become lonely, frozen rogue planets hurtling aimlessly through the vacuum, driven apart by the relentlessly accelerating space between them and their parent star. At this stage, dark energy has defeated all localized gravitational systems entirely. The force of nothingness is demonstrably stronger than the force of mass. Phase 4. Earth's final moments, 30 minutes before the end. The repulsive force now targets the final gravity, the bonds of the planet itself. The force of dark energy overcomes the gravitational self-attraction of the Earth. The planet is ripped into fragments. This is the penultimate stage. The next and most fundamental stage of destruction shifts from the gravitational forces to the forces that govern matter itself, moving to the subatomic realm. The final and most fundamental stage of destruction shifts from the gravitational forces to the forces that govern matter itself, moving to the subatomic realm. This is the point where the expansion of space affects us at a personal, intimate level. The terrifying part happens in the last 30 minutes of the universe's timeline, when the repulsive force turns inward upon matter. 1. Molecular dissolution, the last 6 minutes. The force of dark energy accelerates to the point where it overcomes the electromagnetic bonds that hold molecules together. The complex chemical structures of your body, proteins, DNA, water, are dissolved instantly. Your flesh would turn to gas. Your body would instantly reduce to a cloud of atoms. This is not combustion. It is a cold, violent deconstruction driven by immense negative pressure. This is the precise moment where the rate of expansion between the carbon atoms in your spine surpasses the effective speed of the electromagnetic force that holds them together. Your existence, defined by chemistry and electromagnetism, is erased in moments. 2. Atomic destruction, the final second. In the ultimate microsecond, the force breaches the atomic nucleus itself. Dark energy overcomes the strong nuclear force, the most powerful force in the universe, the one that binds tiny quarks into massive protons and neutrons, is defeated. The protons and neutrons are violently ripped into their constituent quarks. The entire universe would literally dissolve into a final chaotic soup of unconstrained quarks and leptons. Not even light can coherently exist, as the photons themselves are stretched into infinitely long wavelengths. The local speed of expansion exceeds the speed of light even on the smallest scale. The Big Rip is the predicted end where the fundamental constant of causality itself breaks down. There is no longer a defined before and an after, only a moment of infinite density and a sudden, final erasure. The immense physics of this end suggests a problem that is simply too vast for any human-made machine to solve, pushing us to the limits of our scientific investigation. We have tried to find a way to study this energy, to measure its potential, to understand the mechanism that binds our future to the cosmic destiny dial, Omega. The ultimate goal was always to find a theoretical bridge between general relativity, the physics of the very large, which describes dark energy, and quantum mechanics, the physics of the very small, which governs the vacuum. This quest for quantum gravity remains the final frontier of physics. Our greatest tools, like the Large Hadron Collider at the research facility CERN, have allowed us to peer into the high-energy conditions of the universe's first fractions of a second. Our greatest tools, like the Large Hadron Collider at the research facility CERN, have allowed us to peer into the high-energy conditions of the universe's first fractions of a second. This monumental machine confirmed the existence of the Higgs boson, a particle central to the standard model of particle physics. However, even the colossal power of the LHC is insufficient to probe the deep physics of dark energy at its most fundamental level. The Big Rip and the physics of the vacuum itself requires energy levels that dwarf current technology. To truly test the quantum nature of dark energy, the ultimate source of the vacuum energy, we would theoretically need a particle accelerator roughly the size of our entire solar system. The sheer scale of the energy involved makes experimental testing impossible under current human capabilities. This practical limitation means we are constrained by what physicists refer to as the Planck barrier. The Planck era is the theoretical boundary of our current scientific knowledge, 10 to the power of minus 43 seconds after the Big Bang. At this incredibly short timescale, the entire observable universe was compacted into an area smaller than a single proton, and the temperature reached the extreme Planck temperature. This fleeting, chaotic moment is the only time and place where gravity, electromagnetism, and the nuclear forces were theoretically unified into a single, cohesive force. If we could pierce the Planck barrier, we could understand this original unified force that created the universe, and perhaps the mechanism that is now accelerating its destruction.
But the energy required to observe such a realm is fundamentally beyond our technological grasp. The Big Rip, therefore, remains a theoretical threat that is simply too immense for our current instruments to fully resolve.
This state of delicate, transient balance, known as metastability, offers a chilling theoretical scenario. Think of our universe as a marble resting in a slightly elevated hollow at the bottom of a colossal valley. We are secure for the moment in what physicists call the false vacuum state. But the true, absolute lowest energy state of the field, called the true vacuum, is theorized to be much, much deeper. The existence of this deeper minimum means that the current state of our vacuum is not permanent. It is merely temporary. If the Higgs field were ever to be given a sufficient quantum kick, perhaps originating from an extreme physical event, like a catastrophic black hole event or a collision of immense energy far in the cosmos, it could theoretically tunnel to this true lower energy state. This would instantaneously trigger a vacuum decay bubble that would expand outwards at the speed of light. Inside this bubble, the fundamental constants that govern the laws of physics would be fundamentally and instantly changed. Particles would acquire new, arbitrary masses. Chemical bonds would fail instantly. The familiar world would vanish, replaced by a new, unknown reality with entirely different physics. The discovery of the Higgs boson, while a triumph of the Standard Model, also revealed that the universe we inhabit is incredibly fragile, balanced precariously on a razor's edge of quantum probability. The Big Rip scenario, driven by phantom energy, is merely one possible mechanism for the ultimate end. The possibility of a vacuum decay event is another, reminding us that even the most fundamental constants and forces are subject to cosmic variables we do not fully understand. Whether the end comes from the phantom energy of dark energy, a force that accelerates space, or the false vacuum of the Higgs field, a shift in the underlying quantum reality, the universe we call home remains the ultimate time-dependent structure. This inherent instability has fueled deep philosophical and scientific speculation, leading some theorists to ask if our reality is even real at all. The existential threat posed by dark energy and the fragility of the Higgs field have driven the resurgence of a profound, unsettling theoretical framework, the simulation hypothesis.
The idea that our reality might be a simulation suggests a new interpretation for these cosmic parameters. Consider, for instance, the fine structure constant. This dimensionless number dictates the precise strength of the electromagnetic interaction, the force that governs chemistry, light, and the stability of all atoms. If its value were even slightly different, if the value was different by only a tiny fraction of a percent, the universe we know would be fundamentally barren. Stable stars could not form. The complex chemistry necessary for life would fail. In the simulation framework, this constant is simply a variable set intentionally by the programmers. The Big Rip, then, is not a physical force, but a fatal, runaway error in the cosmic programming code. This perspective interprets the various cosmic anomalies as glitches or imperfections in the program's execution. The overrun variable. Dark energy could be interpreted as a variable that the simulator failed to cap or control effectively. It was perhaps intended to be constant, but a slight coding oversight, a misplaced symbol, or a forgotten limit check allows its density to exponentially increase as the universe expands. The Big Rip is the result of the universe being destroyed by a digital memory leak, or an infinite loop in the background process. The secret patch. That vast, inexplicable numerical difference between the theoretical and observed vacuum energy, that stunning mismatch of 1 followed by 120 zeros, is sometimes interpreted as the simulator's desperate last-minute attempt to patch the code in the first microsecond of the Big Bang, just barely saving the universe from instant, total collapse. The universe is a system that shows evidence of rapid post-creation adjustments. If this hypothesis is true, the Big Rip becomes the ultimate, final moment of realization. The simulator is either catastrophically malfunctioning, running a necessary destructive stress test, or simply turning the program off for good. Our ultimate cosmic doomsday is not a natural law, but a digital execution order. We are now compelled to revisit the final, inevitable moments of the Big Rip once more, with this new perspective. The scale and speed of the repulsive force is what makes it so terrifying to comprehend. It tears not just the large, but the intrinsically small, and it does so with a precision that hints at a fundamental, inescapable law. The sheer scale and speed of the repulsive force is what makes the Big Rip so terrifying to comprehend. It tears not just the large, but the intrinsically small, and it does so with a precision that hints at a fundamental, inescapable law, or perhaps a line of flawless code. The Big Rip follows a defined schedule, a systematic dismantling of the universe's structure in reverse order of binding strength.
The history of science is a testament to our struggle to understand and ultimately control the environment around us. Yet with dark energy, we are faced with an environmental factor that is fundamentally beyond our control, a challenge to our very notion of mastery. The profound realization brought by the discovery of accelerated expansion is the ultimate cosmic irony. For centuries, humanity looked up at the night sky and feared the known, visible dangers of the cosmos. We feared the black holes, the asteroid impacts, the stellar explosions. We feared what was out there in the darkness. The great, sobering truth revealed by modern cosmology is that the most powerful, destructive force in the entire cosmos is already here. It is everywhere. It is the very fabric of the void surrounding us, pushing us apart, patiently waiting for the moment to turn its acceleration inward upon us. The discovery of dark energy, once hailed as a major triumph of human scientific endeavor, has quietly become a silent, unspoken reminder of our ultimate insignificance. We are brilliant enough to measure the force, but we are not powerful enough to fight it. We are smart enough to predict the when, but we are not resourceful enough to change the how. The irony is deepest in the ultimate fate of our cosmic architect, dark matter. Dark matter, the invisible glue, the structural foundation of the universe, is not just ignored, but is being actively corrupted by its rival, dark energy. The dark matter halo that was supposed to protect the Milky Way, the stable, dense core built over billions of years, is systematically unwoven by the phantom energy. The architect is not defeated swiftly, it is humiliated, its careful scaffolding stretched and dissolved, unable to transmit the essential force of gravity across the expanding void. This is the ultimate defeat. The force of cohesion is defeated by the force of nothingness. Perhaps the true purpose of dark energy is not destruction, but to serve as a profound lesson in humility. It forces us to confront the very boundaries of our knowledge, the limits of our technology, and the ultimate inescapable reality that the universe is not inherently designed for our survival. It is an indifferent, self-destructing engine, and we are merely the transient energy it expends along the way.
The existence of dark energy challenges us to redefine our place in a cosmos that is actively expanding away from us.
The existence of dark energy challenges us to redefine our place in a cosmos that is actively expanding away from us. Let us take a moment to reflect on the immense loss that the defeat of dark matter represents. Dark matter is the unsung hero, the stabilizing force that for the first 7 billion years of the universe shaped order from chaos. Without it, the initial slight density fluctuations left over from the Big Bang would have been too weak to overcome the rapid expansion of the young universe. Dark matter halos provided the deep gravitational wells necessary to gather baryonic matter, the normal stuff we see, into the first stars and galaxies. It created the cosmic web, a vast sponge-like structure of filaments and voids where galaxy clusters reside. The Big Rip is not just destroying visible galaxies, it is fundamentally dismantling this invisible foundational cosmic web. As the phantom energy accelerates, it acts as a negative tension, literally stretching the space between the points of this web. The filaments, the long strands of dark matter connecting clusters, are the first large structures to break. Once these filaments snap, the gravitational tether that held vast groups of galaxies together is gone. Each galaxy cluster becomes an island, then each galaxy, and finally each star. The defeat of dark matter is particularly poignant because it signifies the end of the universe's ability to create and sustain structure. Dark matter's gravity is what gives objects their mass and pull. Without it, even in the moments before the final atomic rip, objects simply lose their gravitational identity. A black hole, which is essentially an infinitely dense point of gravity, would find its event horizon, the boundary defined by gravity's pull, being pulled apart by the accelerating space. The black hole would effectively evaporate, not through Hawking radiation, but through the overwhelming tidal force of dark energy. This final, comprehensive defeat means that no refuge is possible. There is no star, no planet, and no dense object, even a black hole, that can escape the relentlessly accelerating expansion. The architect's ultimate creation, the entire structured cosmos, is systematically liquidated by the wrecker. Our scientific understanding, therefore, becomes the last act of defiance, a final attempt to document the machine that is executing us.
Our scientific understanding, therefore, becomes the last act of defiance, a final attempt to document the machine that is executing us. We are leveraging the only tools we have, our intellect and our advanced instruments, to chart a destiny we cannot change. Consider the instruments that are currently refining our understanding of this fatal parameter, omega. Projects like the Dark Energy Survey, DES, and the upcoming Euclid satellite mission are focused entirely on meticulously mapping the expansion rate of the universe and the distribution of matter. They do this by observing three main cosmic phenomena: baryon acoustic oscillations, BAO, weak gravitational lensing, and supernova type 1a. Baryon acoustic oscillations are subtle ripples in the distribution of galaxies, remnants of sound waves that traveled through the plasma of the early universe. By measuring the size of these ripples today, astronomers can use them as a standard ruler to measure the expansion of space at different times in the past. This gives a direct measurement of how dark energy's repulsive force has evolved. Weak gravitational lensing is the subtle bending of light from distant galaxies as it passes through the gravitational field of closer massive objects, including dark matter. By mapping this lensing effect across vast regions of the sky, scientists can create detailed maps of the dark matter distribution. By comparing this distribution to the actual expansion rate, they can precisely gauge how dark energy is interacting and challenging the force of gravity. Supernova type 1a, our original standard candles, continue to be monitored with greater precision. They provide the most direct evidence of the cosmic acceleration itself. Every data point collected by these missions is a vote cast for or against the Big Rip.
The entire global astronomical community is effectively engaged in a massive, decades-long effort to read the cosmic destiny dial, refining the value of omega from simply less than -1 to a precise number that determines the remaining cosmic lifespan. It is the most vital, yet ultimately most tragic scientific undertaking in human history.
The dynamic nature of dark energy means the future of the cosmos is not fixed, but hinges on the subtle value of its equation of state, omega. Now we turn our attention to the constant power struggle that defines our existence, the cosmic battlefield defined by dark matter and dark energy. We live in a cosmos defined by a constant, profound tug-of-war between two immense forces that remain invisible to our eyes. Dark matter, which accounts for approximately 27% of the total energy mass, is the architect. It is the invisible scaffolding, the gravitational glue that was instrumental in building the cosmic web. It forms vast, stable halos around galaxies. Without its powerful gravitational attraction, the rapidly spinning galaxies would have simply flown apart. Dark matter represents the force of cohesion. It is the energy that seeks to bring and hold things together, the foundation of all large-scale structure. Dark energy, accounting for the dominant 68%, is the wrecker. It is the force of expansion. It seeks to push everything apart. It represents the overwhelming majority of the universe's content, and its influence on the long-term future is absolute. For the first 7 billion years of the universe's existence, dark matter was largely in charge. Gravity ruled supreme. Galaxies clumped together, forming the magnificent clusters and superclusters we observe today. But around 5 billion years ago, remarkably close to the time our own solar system was forming, the energy density of dark energy finally surpassed the combined matter density. Dark energy had achieved cosmic dominance. The universe entered the dark energy-dominated era, an era of accelerated expansion that continues to define our existence today. Dark matter diligently built the structures, but dark energy simultaneously ensures that every newly formed galaxy cluster is immediately pushed further away from every other cluster, slowly turning the cosmos into a vast, cold expanse defined by ever-increasing distance. But even this cosmic acceleration is merely the initial phase. The Big Rip is the catastrophic moment the Cold War turns hot and dark energy turns its destructive attention from the spaces between structures to the spaces within them. It occurs only if dark energy is phantom energy, meaning its equation of state, omega, is definitively less than -1. This is the doomsday threshold. If omega is less than -1, the crucial physics dictates that the density of dark energy increases as the universe expands. It is a profound cosmic abnormality. It becomes stronger the larger the volume it occupies. It is literally feeding on the very expansion it creates, leading to an exponential and unstoppable acceleration. This force would then sequentially overcome all other fundamental forces one by one. The Big Rip is the predicted end where all 4 fundamental forces are defeated and every single constituent part of the cosmos is violently torn apart.
This legacy of curiosity is an intrinsic part of what it means to be a conscious being in an expanding, mysterious universe. Now let us return to the deepest theoretical paradox, the nature of dark energy itself. Dark energy is not simply a force, it is, in essence, the energy of nothingness. The core mystery remains: how can empty space possess energy? And how can that energy have such a bizarre, repulsive property? When we talk about the vacuum of space, we are talking about a state devoid of all conventional matter and radiation. Yet dark energy demonstrates that this vacuum is anything but inert. The simplest model, the cosmological constant, lambda, suggests that the energy density is fixed. As space expands, the volume increases, and thus the total amount of dark energy increases, leading to accelerating expansion. This is like having a perfect constant energy source embedded in every cubic meter of space. As space grows, the total number of energy units grows proportionally. This model is conceptually simple, but fails spectacularly when compared to quantum field theory, as we discussed with the 1 followed by 120 zeros discrepancy. The alternative, quintessence, suggests that this energy is not fixed but dynamic, carried by a fluid-like field. This is a field whose properties change over time, possibly weakening or strengthening. The Big Rip hinges on this field becoming phantom energy, a state where the energy density increases as the volume increases. To understand phantom energy, imagine a substance with negative mass and negative pressure. If you try to pull it apart, it pulls harder. If you try to compress it, it pushes back harder. It violates the basic energy conditions of physics, but mathematically it remains a possibility within general relativity. The discovery of a confirmed W value less than -1 would fundamentally challenge our understanding of gravity and energy conservation, forcing us to rethink the most basic rules of the cosmos. The most powerful force in the universe is defined by a deep and profound sense of negativity.
The most powerful force in the universe is defined by a deep and profound sense of negativity. Let us delve deeper into this concept of negative pressure, which is the defining characteristic of dark energy. In everyday life, pressure is a positive force. When you pump air into a balloon, the air exerts positive pressure outwards. When light strikes a surface, it exerts a tiny bit of positive pressure. This positive pressure is typically associated with energy density, and it causes matter to attract via gravity or to repel via conventional expansion. Dark energy, however, exhibits negative pressure. Imagine stretching a rubber band. The energy stored in the rubber band's tension can be considered a form of pressure. Negative pressure in this cosmic context is a kind of tension that pulls inward on the vacuum itself. General relativity dictates that the force of gravity is determined by both the energy density and the pressure of the contents of the universe. Positive pressure adds to the gravitational attraction. Negative pressure, conversely, subtracts from it, creating a repulsive gravity. Dark energy has a pressure that is almost exactly -1 times its energy density. This immense negative pressure is what provides the necessary repulsive force to overpower the conventional attractive gravity of dark matter and normal baryonic matter, leading to accelerated expansion. In the Big Rip scenario, this negative pressure intensifies to the point where it becomes more negative than the energy density itself, the W less than -1 condition. This phantom energy represents an extreme theoretical state where the repulsive tension grows exponentially stronger as the universe stretches. It is a runaway feedback loop. The expansion creates more volume, which makes the negative pressure stronger, which causes more expansion, and so on. This unchecked escalation is what moves the threat from a gradual speed-up to an imminent, violent tear. The integrity of the vacuum, the fundamental medium of space-time, is compromised by this runaway negative tension.
The integrity of the vacuum, the fundamental medium of space-time, is compromised by this runaway negative tension. The Big Rip is a calculated sequence of destruction that demonstrates a clear hierarchy of binding forces, starting with the weakest. The first force to be defeated is the gravitational force on the largest scales. This is the weakest of the 4 fundamental forces, and dark energy overcomes it first between galaxy clusters, then between galaxies, and finally between stars and planets. This process defines the macroscopic stages of the Big Rip, spanning millions of years. The second force to be defeated is the electromagnetic force. This force, which is vastly stronger than gravity, is responsible for holding atoms together into molecules and for all chemical bonds. It is the force that defines solid matter and living structures. The expansion rate must accelerate so violently that the space between atoms expands faster than the electromagnetic force can transmit its attraction. This happens in the final minutes, dissolving all complex matter, a cold chemical annihilation. The third and most powerful force to be defeated is the strong nuclear force. This force is the ultimate binder, the glue that holds quarks together inside protons and neutrons and holds the nucleus of an atom together. It is immensely powerful, but its range is incredibly short, limited to the size of an atomic nucleus. In the final microsecond, the runaway negative pressure breaches this shield. The space between the quarks expands faster than the strong force can act, leading to the ultimate disintegration of matter. The ultimate fate is defined by this clear scientific hierarchy. The destruction is not random. It is systematic, calculated, and dictated by the precise binding energy of the fundamental forces themselves. Each step is a scientific milestone marking the defeat of a core law of the cosmos. This orderly, calculated breakdown is perhaps the most unsettling feature of the Big Rip.
Each step is a scientific milestone, marking the defeat of a core law of the cosmos. This orderly, calculated breakdown is perhaps the most unsettling feature of the Big Rip. Let's trace the collapse of gravity in detail, as it provides the longest and most observable portion of the countdown. The destruction begins when the repulsive pressure of dark energy overcomes the average gravitational density of the largest structures in the universe, the superclusters of galaxies. These are loose associations of galaxy clusters, sprawling across hundreds of millions of light years, held together by the weakest collective gravitational pull. Once dark energy wins, these superclusters break apart and their constituent galaxy clusters begin to accelerate away from each other faster than before. Next, the force targets the galaxy clusters, such as our own local group. Dark matter plays a crucial role here, as the gravitational binding is much stronger. However, the accelerating vacuum tension eventually wins, tearing the dark matter filaments and scattering the galaxy clusters into the widening void. The most personal loss under gravity's defeat is the Milky Way's destruction. The gravity of the central supermassive black hole and the galaxy's dark matter halo is immense, but finite. As the dark energy density continues to increase, the repulsive force overwhelms the attractive force. Stars are wrenched from their galactic orbits and flung into the darkening intergalactic space. Our sun becomes a rogue star. Finally, the force targets the solar systems. The orbital dynamics of planets are exquisitely sensitive to gravity. When the repulsive force overcomes the sun's pull, the Earth and its planetary siblings are flung from their orbits. They are no longer bound, traveling alone in an ever-accelerating vacuum. The countdown is now in its final months, and the remaining struggle is internal, against the planet's own mass. The countdown is now in its final months, and the remaining struggle is internal, against the planet's own mass. The gravitational self-attraction that holds the planet's mass together is the final component of gravity to be defeated. As the dark energy density continues to climb exponentially, the repulsive force overcomes the mass of the Earth itself. The planet, no longer able to hold itself together, fragments violently. Mountains crumble, tectonic plates separate, and the atmosphere instantly boils away into the accelerating vacuum. The countdown enters its final minutes, and the destructive focus shifts from the macroscopic force of gravity to the microscopic force of electromagnetism. The electromagnetic force is approximately 100,000 trillion times stronger than gravity. This is the force that defines all chemistry. It holds electrons in orbit around atomic nuclei, and it governs the sharing and transferring of electrons that create molecular bonds. The defeat of this force means the end of all complex matter.
In the final 6 minutes of the universe, the expansion rate of space between atoms exceeds the speed at which the electromagnetic force can act to hold them together. All molecules instantly dissolve. The atoms that form water, protein, and DNA are pulled apart. Any structure, whether biological or geological, is instantly deconstructed into a cloud of its constituent atoms. This is a cold, calculated chemical annihilation. There is no fire, no explosion in the conventional sense. There is only an instantaneous, silent stretching of the vacuum that destroys the intricate geometric architecture of matter. The world is reduced to its basic elemental components, a soup of individual, unbonded atoms, rapidly accelerating away from each other. The atoms themselves are now the last remaining stable structures, clinging to existence through the power of the most short-ranged, yet most powerful force known to science. The atoms themselves are now the last remaining stable structures, clinging to existence through the power of the most short-ranged, yet most powerful force known to science, the strong nuclear force. This force is the final bastion against the Big Rip. The strong nuclear force binds quarks together to form protons and neutrons, and it holds these protons and neutrons together within the nucleus of an atom. Its power is immense, allowing it to overcome the electromagnetic repulsion between positively charged protons crammed into a tiny space. However, its crucial limitation is its short range. It only acts effectively over distances the size of an atomic nucleus. In the final microsecond of the Big Rip, the density of phantom energy reaches an absolute, staggering maximum. The repulsive force becomes so intense that it breaches the perimeter of the atomic nucleus. The vacuum tension accelerates the space between the protons and neutrons faster than the strong force can keep them bound together. The atomic nuclei are violently ripped apart. But the destruction does not stop there. The force then targets the internal structure of the nucleons themselves. The protons and neutrons are composed of 3 quarks each, bound by the strong force. In the ultimate moment, the vacuum accelerates the space between the quarks faster than the strong force can overcome. The quarks, the most fundamental building blocks of matter we know, are instantly freed from their confinement. The universe is reduced to a chaotic, non-interacting plasma of individual fundamental particles, quarks, electrons, and neutrinos. All 4 fundamental forces have been sequentially defeated. The fabric of space-time is stretching faster than the speed of light on all scales, even the Planck length. All causality, all structure, and all memory are erased in this final moment of total, comprehensive annihilation. The universe is gone. All causality, all structure, and all memory are erased in this final moment of total, comprehensive annihilation. The universe is gone. What then is the aftermath of the Big Rip? The answer is a deep, profound nothingness, but a nothingness that is actively expanding. The space is still filled with the remnants of the destruction, individual quarks, leptons, like electrons and neutrinos, and of course, the ever-increasing density of phantom energy. However, these particles are so widely dispersed and accelerating away from each other so fast that they can never interact again. No new atoms can form. No light can travel a meaningful distance. The universe is cold, dark, and utterly devoid of structure. The expansion rate is so extreme that the local speed of expansion exceeds the speed of light, even on the scale of fundamental particles. This means that a particle can never exchange information or even influence its nearest neighbor. The cosmos has broken down into a state of absolute isolation.
In this ultimate scenario, the concepts of time and distance lose their conventional meaning. Since no interaction is possible, the flow of time, which is fundamentally linked to physical processes and change, ceases to have relevance. The final state of the Big Rip is not a stable equilibrium, but an infinitely rapid, unending state of disintegration. The universe has expanded into a kind of static noise, where the only movement is the runaway stretching of the vacuum itself. The ultimate fate of the universe is not the slow, quiet death of the Big Freeze, but a spectacular, violent erasure, leaving behind a cold, featureless void where all fundamental laws have been defeated. This forces us to confront the limits of our understanding of what constitutes matter, energy, and reality itself. The ultimate fate of the universe is not the slow, quiet death of the Big Freeze, but a spectacular, violent erasure, leaving behind a cold, featureless void where all fundamental laws have been defeated. This forces us to confront the limits of our understanding of what constitutes matter, energy, and reality itself. Yet, the possibility of the Big Rip also invigorates the field of cosmology, as it forces scientists to pursue theories that can account for such extreme behavior. The greatest challenge moving forward is developing a theory of quantum gravity that can incorporate dark energy naturally. Current physics operates under two separate pillars: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes matter and forces at the smallest scales. These two theories break down when applied to the most extreme environments, such as inside a black hole, or during the Big Bang's earliest moments, or potentially during the Big Rip. A successful theory of quantum gravity, such as string theory or loop quantum gravity, must be able to resolve the conflict between the accelerating expansion of space and the quantum nature of the vacuum. If dark energy is indeed phantom energy, this implies a breakdown in the basic energy conditions of general relativity. This breakdown suggests that gravity itself, as described by Einstein, must be modified at the cosmic scale. Research is heavily focused on refining the measurement of the cosmic destiny dial, omega. Scientists are racing to determine if the value is truly less than -1, or if it is exactly -1, the stable cosmological constant. New observational missions are designed to be sensitive enough to detect minute variations in W over cosmic time. Finding even a slight deviation from -1 that tends toward more negative values would provide the first definitive evidence that the Big Rip is the inevitable future, fundamentally reshaping the trajectory of cosmological research for centuries. The quest to measure the expansion rate is the quest to define the ultimate limits of physical law.
The quest to measure the expansion rate is the quest to define the ultimate limits of physical law. To fully grasp the nature of dark energy, we must consider its impact on the geometry of the universe. Einstein's general relativity dictates that the distribution of mass and energy determines the curvature of space-time. The Big Bang theory posits three main possibilities for the universe's overall geometry: flat, closed, or open. A flat universe is one where parallel lines remain parallel, like a sheet of paper. A closed universe is positively curved, like the surface of a sphere, and if the expansion stopped, it would lead to the Big Crunch. An open universe is negatively curved, like a saddle, leading to perpetual expansion and the Big Freeze. Remarkably, observations of the cosmic microwave background, CMB, suggest that our universe is nearly flat on the largest scales. This flat geometry is thought to be a remnant of the inflationary epoch, a period of extreme, rapid expansion immediately after the Big Bang. Dark energy adds a new layer of complexity to this geometry. Although the overall space is flat, the phantom energy of the Big Rip creates a kind of dynamic, negative curvature locally by overwhelming the gravitational effects of mass. The repulsive force essentially counteracts all attractive curvature. As the density of phantom energy increases, it dominates the space-time geometry, regardless of the initial flat condition. In the final moments of the Big Rip, the negative pressure of dark energy stretches the local space-time geometry so rapidly that the concept of a smooth, continuous space-time fabric breaks down. The runaway expansion violates the necessary conditions for space-time to be treated as a continuum, potentially leading to the re-emergence of the quantum foam at macroscopic scales, a final catastrophic blending of quantum and relativistic effects. The very stage upon which the universe acts is torn apart.
The very stage upon which the universe acts is torn apart. The scientific race to determine the ultimate fate of the universe is essentially a race against the number 0. Specifically, a race to determine if the value of omega is equal to, greater than, or less than -1. The number, -1, is the critical dividing line. If W equals -1, the universe adheres to the cosmological constant. Expansion accelerates, but the density remains fixed. The universe ends in a cold, quiet, big freeze after an incredibly long time. If W is greater than -1, dark energy eventually dilutes, gravity takes over, and the outcome is the big freeze, only slightly faster than the W equals -1 case. The cosmos fades quietly into thermodynamic equilibrium. The terrifying outcome, the Big Rip, occurs only if W is less than -1. Crossing this threshold means that the energy density increases as the universe expands, leading to a finite, definite date for the total annihilation of all structure. The current observational data places W incredibly close to -1, within a narrow band of uncertainty. This proximity means that scientists cannot yet definitively rule out the Big Rip. The entire precision of modern cosmology is dedicated to shrinking this band of uncertainty, pushing the error bars closer and closer to that critical -1 threshold. If the value is confirmed to be even slightly less than -1, a countdown begins. A value of W equal to -1.5, for instance, would imply a cosmic lifespan much shorter than if W is -1.001. The difference between these minute decimal places represents billions or trillions of years of existence. This sensitivity to tiny numbers underscores the fundamental fragility of our universe's parameters. The precise location of this single decimal point determines whether we have a quiet death or a spectacular, violent erasure.
The precise location of this single decimal point determines whether we have a quiet death or a spectacular, violent erasure. The possibility of the Big Rip forces us to consider the profound implications of having a ghost in the most fundamental equations of physics. The phantom energy that drives the Big Rip violates what physicists call the null energy condition, a cornerstone assumption in general relativity that basically states that the energy density measured by any observer must be positive. Violating this condition implies that the theory of gravity must break down, or that exotic forms of matter with negative mass or negative kinetic energy exist. The idea that the dominant component of our universe is built on a violation of established energy conditions is a deeply unsettling proposition. The history of physics shows that such violations often lead to revolutionary new theories. The discovery of a particle that seemed to violate energy conservation led to the postulation and eventual discovery of the neutrino.
Similarly, the confirmation of phantom energy would necessitate a completely new, more expansive theory of gravity that supersedes general relativity at cosmic scales. This new theory must be able to explain how a negative energy density can be sustained and how it interacts with quantum mechanics without causing immediate collapse. The pursuit of this new physics is driven by the very structures that phantom energy threatens to destroy. Scientists rely on the stable structures, galaxies, stars, and telescopes to observe the forces that are actively trying to dismantle them. This incredible irony motivates the scientific community to push experimental limits, knowing that the answer may lie just beyond our current observational power, waiting for a new generation of telescopes and theoretical models to reveal the truth of the ghost in the equation.
The incredible irony motivates the scientific community to push experimental limits, knowing that the answer may lie just beyond our current observational power, waiting for a new generation of telescopes and theoretical models to reveal the truth of the ghost in the equation. Ultimately, dark energy and the potential for the Big Rip represent the ultimate time bomb. Unlike other cosmic threats, such as asteroid impacts or supernovae, the Big Rip is an internal mechanism, an inherent design flaw in the universe's physics. It is not an external force we can dodge or divert. It is the very expansion of the space we exist in. The metaphor of the time bomb is precise. The moment the acceleration began was the moment the fuse was lit. The rate of the burn is dictated by the value of omega. Every day that passes, the space between galaxies expands further, and if W is less than -1, the density of the destructive phantom energy increases, accelerating the countdown. The clock is ticking on a cosmic scale. While the full countdown likely spans billions of years, the ultimate phases, the dissolution of planets, molecules, and atoms, occur in a terrifyingly brief sequence, months, minutes, and finally, the last second. This rapid end sequence means that once the signs of the final stages begin, no escape or mitigation will be possible. The knowledge of this countdown introduces a profound existential challenge. Humanity has always faced threats, but they have always been bounded by time, distance, or probability. The Big Rip is bounded only by the fundamental laws of physics themselves. The only possible long-term survival strategy would involve developing technology capable of manipulating the fabric of space-time itself, creating localized pockets of reality shielded from the accelerating vacuum tension, a feat currently confined to the realm of theoretical science fiction.
The only possible long-term survival strategy would involve developing technology capable of manipulating the fabric of space-time itself, creating localized pockets of reality shielded from the accelerating vacuum tension, a feat currently confined to the realm of theoretical science fiction. The Big Rip, in a strange way, brings new urgency to solving one of cosmology's oldest puzzles, the horizon problem. The horizon problem asks why the universe on the largest scales is so incredibly uniform. Specifically, why is the cosmic microwave background, or CMB, the afterglow of the Big Bang, almost exactly the same temperature, approximately 2.7 degrees Kelvin, across the entire sky? In a universe that is nearly 14 billion years old, distant regions of space should never have had time to interact or exchange heat information, as this would require energy to travel faster than light. These regions are outside of each other's horizon. The standard solution to the horizon problem is the theory of cosmic inflation, a period of extreme exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched a tiny, uniform patch of space-time into the entire observable universe. This solved the problem by ensuring that all parts of our visible universe were, at one point, close enough to reach thermal equilibrium. The Big Rip
driven by phantom energy, in a strange way brings new urgency to solving one of cosmology's oldest puzzles, the horizon problem. The study of the Big Rip is, therefore, also the study of the Big Bang's earliest moments, leading to the theoretical search for a new fundamental interaction: the existence of dark energy, particularly if it is confirmed to be phantom energy, suggests that the universe may be governed by more than the four known fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. The hypothetical fluid of quintessence, or the mechanism driving the cosmological constant, could be manifestations of a fifth fundamental force, often referred to generally as quintessence. This force would be incredibly weak at small, local scales, which is why it has escaped detection in laboratory experiments. However, its influence would dominate on the largest, cosmic scales, driving the accelerated expansion. The properties of this hypothetical fifth force are constrained by dark energy's behavior. It must have a field associated with it that permeates all of space. Crucially, its interaction with conventional matter must be minimal, or we would have detected it. The strength and range of this force must be such that its repulsive effect is only noticeable over millions of light years, where the influence of gravity begins to weaken. Developing a theory for this fifth force would revolutionize the standard model of particle physics, which currently describes the strong, weak, and electromagnetic forces. The inclusion of a fifth force, particularly one with the extreme negative pressure required for the Big Rip, would necessitate a major revision of how energy and matter interact. It would provide the ultimate proof that our current understanding of the physical world is only a partial view, dominated by the forces that affect our local, familiar environment, while neglecting the dominant but subtle force that shapes the cosmos's destiny. The inclusion of a fifth force, particularly one with the extreme negative pressure required for the Big Rip, would necessitate a major revision of how energy and matter interact. It would provide the ultimate proof that our current understanding of the physical world is only a partial view, dominated by the forces that affect our local, familiar environment. The threat posed by dark energy is a crisis of scale, the cosmic scale of fear. We naturally perceive and react to threats on a human scale: fires, floods, or political conflicts. We have developed technologies and societal structures to mitigate these local, bounded dangers. Even a global event, like a large asteroid impact or a massive supernova explosion, is a physically bounded threat that occurs at a specific time and location. The Big Rip is different. It is an unbounded, pervasive threat. The threat is everywhere simultaneously because dark energy is everywhere simultaneously. There is no direction to flee, no shield to deploy, and no warning that can be given that is early enough to be acted upon given the final, rapid stages of dissolution. This lack of boundaries makes the threat uniquely difficult for the human mind to process. Furthermore, the Big Rip operates over geological and cosmological timescales that dwarf human existence. While the end is guaranteed, the vastness of the countdown shields us from the emotional urgency of the threat. This contradiction, the certainty of total annihilation, juxtaposed with the immense timescale, is a defining feature of our current cosmic dilemma. The knowledge is intellectually terrifying, but emotionally distant. Our descendants, however, will face a reality where the emotional distance has collapsed, and the countdown has accelerated to their local, recognizable timeframes. The scientific detachment we maintain today is a luxury granted by the Big Bang's initial momentum, a luxury that will eventually expire.
The scientific detachment we maintain today is a luxury granted by the Big Bang's initial momentum, a luxury that will eventually expire. The Big Rip scenario presents a fascinating paradox for the most extreme objects in the universe: black holes. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape.
They represent the ultimate triumph of gravitational collapse. However, their existence relies entirely on the local strength of gravity overpowering all other forces. In the Big Rip, the accelerating negative pressure of dark energy directly challenges this supremacy. As the repulsive force increases exponentially, it acts against the gravitational attraction that holds the black hole's event horizon together. The event horizon is the boundary defined by gravity's influence. As space accelerates, this boundary is pulled apart. Theoretical models suggest that the size of the black hole's event horizon effectively shrinks as the repulsive force increases. Eventually, the expansion rate of space across the event horizon exceeds the speed of light, meaning the vacuum itself is pulling the space faster than the gravity can hold it. The black hole would effectively evaporate in a process fundamentally different from Hawking radiation. Instead of losing mass slowly through quantum effects, it would be instantly torn apart by the overwhelming tidal forces of dark energy. This suggests that even the most gravitationally dominant structures are not immune to the pervasive expansion. The ultimate gravitational victor, the black hole, becomes the penultimate victim of the accelerating vacuum tension. This defeat underscores the total, comprehensive nature of the Big Rip, leaving no corner of the cosmos safe. The black hole would effectively evaporate in a process fundamentally different from Hawking radiation. Instead of losing mass slowly through quantum effects, it would be instantly torn apart by the overwhelming tidal forces of dark energy. This defeat underscores the total, comprehensive nature of the Big Rip, leaving no corner of the cosmos safe. The accelerating expansion also dictates the ultimate fate of light. In our current universe, light, photons, travels at the speed of light, allowing us to see distant galaxies. The universe's expansion stretches the wavelength of this light over time, causing distant galaxies to appear redshifted. This is how we know the universe is expanding. In the Big Rip, this stretching effect becomes extreme. As dark energy density increases, the expansion accelerates to the point where the space between our eyes and a distant star expands faster than the light can travel. Distant objects appear to accelerate away from us faster than the speed of light, effectively disappearing beyond our cosmic horizon. In the final minutes of the Big Rip, this effect becomes localized. The light emitted by nearby stars, even our own sun, would be stretched so dramatically that it would become infinitely redshifted. The photons would lose all their energy to the expansion of the vacuum. The entire sky would instantly go black, even though stars and light sources still exist for a few more minutes. The universe loses its ability to transmit information, plunging the remaining matter into instant, absolute darkness. In the final second, when the atoms and quarks are ripped apart, the light associated with those fundamental particles would also be stretched into infinite wavelengths. The light that defines our reality, the fundamental carrier of the electromagnetic force, is erased by the relentless negative pressure of the vacuum. The final act of the universe is an instantaneous, silent, and total plunge into non-existence.
The final act of the universe is an instantaneous, silent, and total plunge into non-existence. Let us fully inhabit that incomprehensible moment, the final second. This is the point where the expansion rate between two infinitesimally close points exceeds the speed of light. The scale of the repulsive force is astronomical, even when applied to the smallest distances. Microsecond 0-6. The electromagnetic force is defeated. All atoms, though still intact, are now unbonded. The concept of solid or liquid matter is meaningless. The entire observable universe is a chaotic gas of unbonded atoms rapidly accelerating away from each other.
Microsecond 0-1. The strong nuclear force is defeated. The vacuum tension overcomes the force binding quarks within the protons and neutrons. Matter as we know it ceases to exist. Quarks, electrons, and neutrinos are the only remnants. Microsecond 0. The space between the quarks and electrons accelerates at its maximum, theoretically infinite rate. The density of phantom energy peaks, and all remaining fundamental particles are instantly stretched to the point where they can no longer be defined as localized entities. The concept of measurement of time, distance, or mass becomes impossible. The physical constants, such as the speed of light and the Planck length, which define the limits of our reality, are overwhelmed by the speed of the vacuum expansion. The universe effectively stops making sense. All information about the prior existence of structure, from the cosmic web to the fundamental particles, is erased from the fabric of spacetime. The Big Rip is not a transition to a new state. It is the instantaneous cessation of all states, leaving behind only the ever-stretching, infinitely dense negative pressure of the void. The Big Rip is not a transition to a new state. It is the instantaneous cessation of all states, leaving behind only the ever-stretching, infinitely dense negative pressure of the void. This profound fate presents an epistemological challenge, a crisis in what and how we can know about reality. The very possibility of the Big Rip forces us to question the reliability of the physical laws we use to describe the universe. If dark energy can violate fundamental energy conditions and lead to the defeat of all other forces, it suggests that our current framework, general relativity, is incomplete at a fundamental level. Our knowledge, built on the assumption that certain physical laws are constant and inviolable, is fundamentally challenged. The challenge is amplified by the sheer distance of the event. We are trying to predict the ultimate fate of the universe based on minute, fractional measurements of the acceleration rate of very distant objects, Type 1a supernovae. This dependence on indirect, subtle evidence means that the certainty of the Big Rip rests on the precision of instruments and the validity of theoretical extrapolation. Furthermore, the Big Rip highlights the limits of human perception and imagination. We can conceptualize the breakdown of a planet or a star, but we cannot truly grasp the dissolution of the atomic nucleus or the stretching of space-time beyond the Planck scale. Our intellectual models are pushed to the point of absurdity, forcing physicists to rely on abstract mathematical concepts that defy visualization. The Big Rip is the ultimate theoretical extreme, serving as a boundary condition for all future theories of the cosmos.
The Big Rip is the ultimate theoretical extreme, serving as a boundary condition for all future theories of the cosmos. In the face of this total, predicted annihilation, the final value of human existence rests on our legacy of understanding. If the Big Rip is the guaranteed end, what is the meaning of our scientific endeavor? It is not to survive, but to document. Our purpose becomes the comprehensive charting of the universe's life cycle, from its rapid birth during inflation to its violent death by expansion. This documentation is the final act of a self-aware species, the completion of the cosmic narrative. We are dedicating vast resources, through missions like the Dark Energy Survey and the Euclid satellite, to precisely measure the parameters of our doom. This is the ultimate intellectual victory, to fully understand the mechanism that will destroy us. The knowledge itself is the legacy. Even if the Big Rip erases all physical records, the abstract knowledge gained, the understanding of how and why the universe chose this particular path to non-existence, remains the pinnacle of our intellectual achievement.
This documentation may have a practical, albeit theoretical purpose. If other self-aware civilizations exist in other regions of the universe, and if they too face a similar ultimate fate, our data could serve as a warning or a theoretical benchmark. Our final message is not a plea for rescue, but a data set. We were here. We understood the end. This is how the acceleration works. Our existence, framed by the certainty of the Big Rip, gains meaning through this final, necessary contribution to cosmic knowledge.
Our existence, framed by the certainty of the Big Rip, gains meaning through this final, necessary contribution to cosmic knowledge. The very idea of leaving a record implies an audience, suggesting the importance of a final message. If a civilization were fully aware of the Big Rip's timeline, their last act might be to construct the most durable, time-resistant communication probe possible. This probe would not be intended to survive the final atomic tear, but rather to survive the initial phases of the Big Rip, the separation of galaxies, and the loss of the cosmic horizon. The goal would be to transmit the essential data, the value of omega, the composition of dark energy, the observed hierarchy of force defeat, and the full standard model of particle physics. This message would be broadcast on redundant, powerful, low-frequency radio waves, or perhaps encoded in the very structure of highly stable matter designed to survive the initial solar system dissolution. The message is simple: the final testament of humanity's intellectual journey. The ultimate irony is that for this message to be received, it must be intercepted by a civilization that either exists in a region of the universe not yet fully dominated by dark energy, or one that has already developed the technology to manipulate space-time and shield its local environment from the acceleration. Our final communication is a beacon of profound scientific knowledge cast into an increasingly hostile and information-isolated cosmos. It is the final philosophical statement on our relationship with the universe, a statement of understanding, acceptance, and a final, desperate hope for intellectual continuity. It is the final philosophical statement on our relationship with the universe, a statement of understanding, acceptance, and a final, desperate hope for intellectual continuity. The Big Rip forces us to reconsider the very notion of unfolding reality. We commonly think of the universe as a container in which events happen. Dark energy challenges this view by suggesting that the container itself is an active agent, accelerating and ultimately destroying the contents. This means that the reality we perceive is not static, but dynamically changing its fundamental parameters. The current epoch of the universe, dominated by accelerated expansion, is a relatively recent phenomenon, starting around 5 billion years ago. The Big Rip would be the final phase transition, a shift from a state of expansion to a state of dissolution. This transition is governed entirely by the value of omega. A universe where omega less than -1 is fundamentally unstable, programmed for a final, catastrophic failure. This means that the reality we inhabit is transient, and its ultimate fate is encoded in the physics of the vacuum itself. The study of dark energy is not just a study of an external force. It is the study of the universe's internal, fundamental programming and the inevitability of its scheduled obsolescence. The study of dark energy is not just a study of an external force. It is the study of the universe's internal, fundamental programming and the inevitability of its scheduled obsolescence. In the face of this cosmic guarantee, the question of mitigation remains a profound, albeit mostly theoretical, area of inquiry. Could an advanced civilization, aware of the Big Rip, find a way to shield itself? Since dark energy is the stretching of the vacuum itself,
Any solution must involve locally altering the properties of space-time. One highly theoretical concept involves creating a localized, stable region of space-time, a kind of cosmic bubble or anti-expansion field. This would require generating a field with a highly positive pressure to locally counteract the negative pressure of dark energy. Essentially, creating a pocket where omega is locally forced to be W greater than -1. The energy required to maintain such a field would be immense, requiring technology capable of harnessing the energy output of entire galaxies. Another avenue is the theoretical development of warp drive or Alcubierre drive technology. These concepts involve manipulating space-time to travel faster than light. If such technology could be achieved, it might offer a means of rapidly transporting a civilization to a region of the universe where dark energy's influence is still negligible, or perhaps even outside the accelerating domain altogether. Although finding such a sanctuary is highly improbable given the pervasive nature of the force. The pursuit of mitigation technology, even in theory, is a reflection of the deep-seated human drive to overcome existential threats, regardless of their scale.
The pursuit of mitigation technology, even in theory, is a reflection of the deep-seated human drive to overcome existential threats, regardless of their scale. The Big Rip also profoundly impacts our ability to observe the cosmos, leading to the silence of the future. Even before the final violent stages, the accelerating expansion will sever our observational ties to the distant universe. As the space between our Milky Way and distant galaxy clusters expands faster than the speed of light, the light from those clusters will never reach us. They will permanently recede beyond our cosmic horizon. Trillions of years from now, long before the Big Rip's final second, future astronomers would look up at a sky that is overwhelmingly empty. All distant galaxies would have vanished, redshifted out of existence. The only visible structures would be the few hundred galaxies in our own gravitationally bound local group. The universe, from their perspective, would appear small, static, and profoundly lonely. This observational isolation has serious implications for future science. Without access to distant light, future civilizations would be unable to observe the early universe, the distribution of matter on the largest scales, or the remnants of the Big Bang itself. They would be blind to the evidence that proved the theory of the expanding universe, the existence of dark energy, and the ultimate fate. Our data, meticulously collected today, is a precious, time-sensitive record of a vibrant cosmos that will eventually go silent. The Big Rip not only destroys matter, it destroys the capacity for cosmic discovery. Our data, meticulously collected today, is a precious, time-sensitive record of a vibrant cosmos that will eventually go silent. The Big Rip not only destroys matter, it destroys the capacity for cosmic discovery. This brings us to the core irony of discovery. The discovery of cosmic acceleration in 1998 was one of the greatest intellectual achievements of the 20th century. Yet this achievement fundamentally limits the intellectual potential of future civilizations. The very act of measuring our universe's expansion revealed a force that guarantees the future universe will be epistemologically impoverished, blind to its own history. The irony is twofold. First, we, living in the brief, fortunate window when the universe is both expanding and transparent, are the only ones capable of gathering the data necessary to solve the cosmological puzzle. Second, the knowledge we gain, the value of omega, is the very knowledge that predicts the end of all future inquiry. Our golden age of cosmology is defined by the discovery of the force that guarantees the dark age of the future cosmos. This places a heavy burden of responsibility on today's scientists. They must not only gather the data, but ensure that the interpretation and significance of that data are preserved in a way that transcends conventional scientific records. The knowledge of the Big Rip is a powerful tool, but it is also a potential source of cosmic despair. Balancing the pursuit of this profound truth with the preservation of societal stability remains a complex ethical and scientific challenge. The final stages of the universe's life demand the highest levels of intellectual honesty and foresight.
The final stages of the universe's life demand the highest levels of intellectual honesty and foresight. The certainty of the Big Rip introduces a unique concept, the physics of cosmic despair. This refers to the psychological and philosophical impact of knowing that the universe is fundamentally unstable and actively programmed for self-destruction. Unlike threats that can be mitigated through human action, the Big Rip is a guaranteed, non-negotiable reality. This can lead to a sense of cosmic nihilism, where all human achievements are rendered meaningless by the inevitability of the final atomic tear. However, the scientific response to the Big Rip is the very antidote to this nihilism. Instead of succumbing to despair, scientists responded by doubling down on inquiry. The Big Rip did not end cosmology. It gave it a definitive, ultimate goal. The very act of measuring and understanding the mechanism of our doom transforms the inevitable destruction from a meaningless event into a profoundly meaningful one, the completion of the ultimate scientific experiment. The intellectual acceptance of the Big Rip is a philosophical maturity test for humanity. It challenges us to find meaning not in permanence, but in process, not in survival, but in understanding. The knowledge of our transient existence against the backdrop of an indifferent, self-destructing cosmos elevates the value of every moment of conscious inquiry. The Big Rip is the ultimate reminder that the value of our civilization lies not in its duration, but in the depth of its curiosity.
The Big Rip is the ultimate reminder that the value of our civilization lies not in its duration, but in the depth of its curiosity. Let us now consider the sheer energy cost of the Big Rip. The total energy required to dissolve all matter in the universe, to break every atomic bond, every nuclear bond, and every gravitational tether is immense. This energy is provided by the destructive density of the phantom energy field itself. As the space expands, the density of phantom energy increases, and this energy is converted into the repulsive force required to defeat the fundamental forces. The total energy of the universe, which is the sum of matter energy, radiation energy, and dark energy, is constantly changing in this scenario. The concept of energy conservation, a bedrock principle of physics, is fundamentally challenged by the Big Rip. If the density of phantom energy increases as the volume increases, it suggests that new energy is being spontaneously generated from the vacuum itself. This means that energy is not conserved on the cosmic scale. The violation of energy conservation is a direct and terrifying consequence of the W is less than -1 condition. This non-conservation implies that the universe, in its final throes, becomes an engine of spontaneous creation, but of repulsive force, not matter. The Big Rip is fueled by a violation of one of the most sacred laws of physics. Understanding the precise way in which energy conservation is violated is one of the final theoretical goals of modern cosmology, as it holds the key to the ultimate nature of the vacuum.
The Big Rip is fueled by a violation of one of the most sacred laws of physics.
Understanding the precise way in which energy conservation is violated is one of the final theoretical goals of modern cosmology, as it holds the key to the ultimate nature of the vacuum. The entire scenario represents the ultimate test of physics. The Big Rip provides an extreme environment against which all candidate theories of quantum gravity and new physics can be tested. A successful theory must be able to resolve the 10 to the 120th discrepancy of the vacuum energy, naturally allow or forbid the W is less than -1 condition, phantom energy, explain the violation of energy conservation without introducing mathematical paradoxes, predict the exact hierarchy and timing of the defeat of the 4 fundamental forces. The Big Rip is the theoretical laboratory where our most ambitious concepts, string theory, loop quantum gravity, and modified gravity models, are pushed to their absolute limits. If a theory fails to account for the possibility or mechanism of the Big Rip, it is likely an incomplete description of the cosmos. The eventual confirmation or refutation of the Big Rip will therefore be the most defining observational event for 21st century theoretical physics. The universe itself is providing the ultimate exam.
The universe itself is providing the ultimate exam. If the Big Rip is confirmed, the immediate theoretical priority shifts to the search for antidotes. This search focuses on physical mechanisms that could, in theory, cause the value of omega to rebound or change before the final stages. A candidate antidote must be a field or particle that would naturally cause the negative pressure of dark energy to weaken over time. One such theoretical antidote involves a highly complex version of the quintessence field, where its equation of state, omega, is not fixed but changes over cosmic history. This field might initially exhibit W less than -1 behavior, driving the acceleration, but eventually evolve to cross the critical threshold, moving toward W greater than or equal to -1. If the field were designed to cross this line before the final atomic tear, the Big Rip would be averted, reverting the universe to the Big Freeze scenario. However, the physics of such a rebounding field is highly speculative. It would require fine-tuning of the field's potential energy and coupling to matter.
Finding such a mechanism would not only save the universe, but would reveal a profound, hidden layer of stability that currently eludes our mathematical models. The final philosophical reflection on the Big Rip centers on the concept of the last true sky. We, the inhabitants of this fortunate cosmic era, are privileged to witness a sky filled with billions of galaxies. We can observe the vibrant history of the universe through powerful telescopes like the James Webb Space Telescope, seeing light that has traveled for billions of years. This richness is a temporary luxury. As dark energy continues its work, the sky our descendants see will gradually empty. Distant galaxies will fade, disappearing beyond the ever-accelerating cosmic horizon. The sky will become dark, silent, and overwhelmingly lonely, containing only the few dozen or few hundred galaxies of our immediate local group. Our era is the last time any self-aware civilization will be able to prove, through direct observation, the scale and history of the cosmos. The knowledge we gather now, the data that proves the Big Bang, the existence of dark energy, and the inevitable Big Rip, is a time capsule. It is a record of a cosmos that existed in its full glory. We are the final witnesses to the entire grand narrative. The Big Rip is the price of admission to this final, ultimate cosmological truth. The value of the stars we see tonight is immeasurable, for in the deep future, they will be gone. The value of the stars we see tonight is immeasurable, for in the deep future, they will be gone. The story of dark energy and the potential for the Big Rip is the most profound narrative in all of science. It is a story that began with a moment of surprise in 1998, when astronomers discovered the ultimate force of repulsion. It is a story that spans billions of years, charting the collapse of gravity, the dissolution of matter, and the end of the four fundamental forces themselves. It is a story that ends in a total, systematic annihilation, leaving behind only the stretching, negative pressure of the void. The knowledge of the Big Rip is our intellectual inheritance, a testament to the fact that we sought and found the final limits of our existence. We are the last generation to see the full, glorious sky and to chart the course of our own destruction. This noble pursuit of understanding, in the face of inevitable non-existence, is the ultimate meaning of human curiosity. The end is coming. It is invisible, it is everywhere, and it is accelerating. Our duty is not to escape, but to understand.